Hello students, in this video we learn about extrinsic semiconductors. Extrinsic semiconductor means they are not pure semiconductors, they have some added impurities. So first of all, why we need to add impurities? If you consider a pure semiconductor, it has very less charge density. That means number of charge carriers in unit volume are very less in semiconductor compared to conductors. So we cannot use these semiconductors for conducting current. Because of that reason, we need to improve the charge density. That means number of charge carriers per unit volume. So one way of improving this charge density is adding impurities. Adding impurities to a pure semiconductor is called doping. So we dope semiconductors in order to increase its charge density, number of charge carriers per unit volume. Depending on the type of impurities we are adding, we can classify these semiconductors into two types. One is N-type semiconductor, another one is P-type semiconductors. As impurities are added to these semiconductors, they are called as extrinsic semiconductors. So first we will learn N-type semiconductor. In general, if you consider a semiconductor, for example, if you take silicon, silicon is tetravalent atom. That means it contains 4 electrons in its valence orbit. That is why it is called as tetravalent atom. So now here in N-type semiconductor, we use impurities as pentavalent impurities. Pentavalent means, penta means 5. They contain 5 electrons in their valence orbit. The examples for pentavalent impurities are phosphorus, arsenic, antimony. These are the examples of pentavalent impurities. Now we will discuss what happens when you add these pentavalent impurities to a tetravalent semiconductor. It is shown graphically in a given diagram. You can see here. So in this diagram you can see silicon atoms as well as phosphorus atom. So now try to understand what they form. When a phosphorus atom, because it is impurity and it is introduced very less in number, we are considering that for 8 silicon atoms, let us say we introduced one phosphorus. Now you know silicon is tetravalent, that contains 4 valence electrons, and phosphorus is pentavalent, it contains 5 electrons in valence orbits. And out of these 5, 4 electrons are phosphorus. 4 valence electrons of phosphorus, they form bonds with 4 adjacent silicon atoms. 4 bonds are formed. Now, but one electron of the phosphorus remains outside because there is no other electron to form a bond with it. All the surrounded atoms are formed already 4 bonds. So one electron is left unbounded, and we call that electron as free electron. It is free electron. As it is unbounded, it can go anywhere it wants. So like this, if you add a small amount of phosphorus impurity to a semiconductor, then it can generate some millions of electrons, free electrons, because a small amount contains some millions of phosphorus atom. So millions of phosphorus atoms can generate millions of free electrons. These free electrons are called donor electrons because phosphorus is ready to donate this electron, to give away its electron, because giving away this electron makes it stable as four bonds are fulfilled. That is why these electrons are called donor electrons, and these impurities are called donor impurities. Now, in this way, if you consider an n-type, why we are calling n-type? Because it generates electrons which are negatively charged. So we call this semiconductor as negative or n-type semiconductor. In this semiconductor, electrons are majority charge carriers and holes are minority charge carriers, because most of the n-type semiconductors have millions of electrons already generated. So electrons are majority charge carriers. They play main role in conducting current in n-type semiconductors. And we can note the following 2 points in this. Here, the number of electrons in conduction band are greater than number of holes in valence band, because number of electrons are majority carriers, and the Fermi level lies just below the conduction band, because majority charge carriers are here electrons. Now let us move to p-type semiconductor. P-type semiconductor, as the name itself implies, it is positive type. Positive type means in semiconductor we can treat hole as a positive charge carrier. P-type semiconductors, the majority charge carriers are holes and minority charge carriers are electrons. Now we will see how holes become majority charge carriers in p-type semiconductor. Consider a silicon which is a tetravalent atom, and here we consider the impurities at trivalent impurities. Trivalent means they contains 3 electrons in outermost orbit. The examples for trivalent atoms are boron, gallium, aluminum and indium, right? So when you add these impurities to pure semiconductor, then it generates holes. Let us see how. Here we know that silicon is tetravalent and impurity we are considering here is boron. Let us say for 8 silicon atoms we introduced one boron atom, and the boron contains 3 valence electrons. 3 electrons, let us say, formed 3 bonds with adjacent silicon atoms, but one of the adjacent atom has no electron to form a bond with it. Here you can see as silicon is giving 1 electron, boron is not giving any electron because it is not having any electron to form a bond. Here this boron is ready to accept 1 electron so as to form the bond and get stabilized. Because of that reason, boron and trivalent impurities are called acceptor impurities, because these impurities readily accept 1 electron to stabilize themselves. In this way, a small amount of boron, suppose if you add small milligrams of boron, then it can generate some million number of free holes. So in this way, adding of trivalent impurities to pure semiconductor generates free holes. In this way, in p-type semiconductor, the majority charge carriers are holes and minority charge carriers are electrons. Because of that reason, this semiconductor is called p-type semiconductor. And you can note the following. Here the number of holes in the valence band are greater than number of electrons in conduction band, and the Fermi level lies just above the valence band because here the majority charge carriers are holes.